Lunch today was really good, so I don't blame you if you fall asleep during my talk, especially since I'm used to it. When I'm teaching classes, all my students are sleeping too, so it's okay. Oh, there you go.
Let's get started. Welcome to session 4, Specialized Hardware and Accelerator Design, LCTES. And hope you guys enjoyed our lunch. As Scott, our first speaker, Scott, mentioned. Scott is going to introduce his research paper, Can Fine-Grained Multithreading Subsume VLIW?
Right. Thank you. I appreciate it. So yes, I'm Scott Pomerville. This was a paper in conjunction with Michigan Tech and Florida State as well. I'm from Northern. This is an homage to, the title is an homage to Can Data Flow Subsume von Neumann computing. So if you know the history of that, the answer ended up, of course, now you know, is no. So don't assume I'm promising the moon because the answer might be no. But we're going to try our best to convince you that there might be a case here. So really quick, we'll just jump through here and just give a background because VLIW, it's a thing we don't really think about every single day. But this is kind of what a VLIW looks like if you squint really hard. So over here, you can see an instruction stream. And this is a 3-wide VLIW. Oftentimes VLIWs are powers of 2, but this one, I'm just trying to illustrate it. And each, essentially, instruction is a bundle of operations. So you have an add, a subtract, and a load word as part of an instruction. Then the next instruction might be a store, a multiply, and a no-op. And each instruction is going to end up essentially getting fetched by this fetch unit, and then the first third might go into this sort of pseudo pipeline here. The second one goes into kind of this pipeline here, and the third instruction would go into this pipeline here, or vice versa. So, or something like that. So the idea basically, though, is that a VLIW processor is much simpler than what we consider our modern superscalar processors, and these instructions are going to have to be essentially set up in a way, or these operations are going to have to be scheduled by our compiler. To maintain alignment, we oftentimes pad these instructions out with no-ops, although we try to then compress them afterwards with specialized hardware. But that's the basic idea and very simple version of a VLIW. And we're really only going to be talking about the basic versions here today. So the motivation here is really, with VLIWs, parallelism is bundled with sort of this instruction representation. VLIWs have these no-ops, and compiled code really needs to match VLIW width. So if I have a 4-wide or 8-wide VLIW, I need to make sure my code matches that width exactly, or have, again, special hardware that's going to modify, for instance, the PCs, or the PC increment, to handle different width code, which means we have to have specialized hardware for backwards compatibility. But what if we have a different encoding? What if we consider that this might not be the only way to represent parallelism statically? New representation might have some potential to handle some of these problems natively, and also, while we're at it, might give us some new avenues for research. So instead, well, what's another way we oftentimes do it? Oftentimes we use multi-threading, and that's really nice, but requires some extra intervention. So instead, though, what if we just take these VLIW packs and treat them as lockstep threads instead? So here I have some instructions here, and I've just sort of removed the actual instructions and replaced them with I1, I2, I3. And so you can see here, or operations. What if instead we just have multiple PCs? Each one is going to run sort of in parallel in lockstep. You notice each lane has its own PC. And then what happens if we then apply maybe some simple synchronization mechanisms, just the ability for lanes to just turn off and on again when they're just told to. In that scenario, what we find is that we can basically eliminate most of the no-ops, if not all of them. At least, that's kind of the hope. And so what we're going to do is essentially treat these sort of individual sort of pseudo-threads as a different stream, but each one is going to represent sort of the different parallelism, or the parallelism that a VLIW would by using long instructions instead of using these synchronized threads. So what we're going to do is really add just a quick piece of terminology here, this idea of a lane. And a lane is really just sort of this pseudo thread coupled with the corresponding hardware that it's going to run. Because if we remember that VLIW has one single fetch unit and then a bunch of essentially just simple pipelined processors that share a register file. The idea is instead, let's just make sure that each sort of pseudo thread has its own individual fetch unit and go from there. We're going to define lanes essentially as being in one of three states. An active lane is just going to fetch instructions from whatever its corresponding stream of instructions are and run them like we expect. There's suspended lanes, and a suspended lane is one where what we'll do is we'll just say, hey, if you're running and you suspend, don't fetch or do any instructions there. And so that'll allow us to essentially not have to encode those instructions. And then in a halted or an active lane, it's just a lane we never turned on. It doesn't actually have a corresponding instruction stream. It's just the hardware that's shut off. To prevent deadlocks in this sort of pseudo multi-threaded situation, we'll have lane 0 be always active, and every other lane we'll refer to as like 1+, essentially. And those ones can turn off. And this entire architecture, the corresponding hardware, as well as sort of this instruction representation, is going to be referred to as a synchronized lane architecture, because I'm not really good at naming things, all right? So the most significant bit is actually going to be one of the most important parts, and we're going to talk about that a little bit in a moment. The ISA that we provided is actually a from-scratch ISA. It looks a lot like MIPS, because I might as well use something that mostly exists so that I don't have to do everything from scratch. But it is its own ISA. We call the SLA ISA. And it has a bunch of instructions all dedicated to spinning up instruction streams, as well as halting instruction streams as we go, entering functions, and so on and so forth, because a couple things are going to change. We won't be able to get into that, but if you're curious, you can read about it in the paper. We have several registers as well that are also just really there to administratively be like, are you running or are you not running, right? For states, as well as if we enter a function, normally we have to keep track of one PC. Now we have to keep track of a handful of PCs. So we have extra registers for that. The main kind of important part, though, is this idea of being able to turn on and off lanes, which is really just a single bit in the instruction set that we call the suspend resume bit or an SR bit. A suspend resume bit sits as the most significant bit of any instruction, and that way we don't have to decode the instruction to know if that bit is set. We can simply use it, and the idea here is I'll just add a .sr in my assembly to say, hey, this bit is set or not set. So all instructions basically have two versions, one where it's not set and one where it is set. So an addu would become addu.sr. And that just says, when you fetch this instruction, don't fetch any more instructions. You're done, and you'll suspend. At least that's true for lanes 1 and so on. So if they see that, that's just the last instruction you're going to run. It'll run through the pipeline and do what it does normally, but it will no longer fetch instructions, and it suppresses any access to the instruction caches, and each lane has its own individual instruction cache. Lane 0 has a .sr extension, but since it can't turn off, all it says is all other lanes that are currently suspended but still have a PC, resume execution. Halted and inactive lanes do not have a PC, so they won't continue. So that's the basic idea of these SR bits. For branches and jumps, because each lane has its own kind of thing going on, we need to make sure that when a branch is taken, all of the lanes update their PCs, but it would be terrible to duplicate all of those branches and have a whole branch taken buffer for each lane. So instead, we offer just a single register called a prepare branch register that just stores a PC. And whenever a lane encounters a special instruction called a PB instruction, it just puts a value in that register. And whenever lane 0 takes a jump, all other lanes that are suspended update their PC to whatever that PC is in the prepare branch register. So that's the basic kind of concept there. When entering a function, all lanes kind of halt, just to make sure that the processor is in a predictable state. They all lose their things except for lane 0, and lane 0 begins execution right away. So the basic idea is then lane 0 will be in charge of starting up new instruction streams to regain that parallelism that we want. One advantage of this scheme is that since entering a function halts all lanes, the processor, if you have some, let's say, a 4-wide processor, and you hand it 2-wide code, or a code that's designed for a 2-lane processor, those 2 lanes that are never used simply never spin up, and so the code actually natively is supported by code for smaller processors is natively supported by ones for larger processors. We just don't utilize the full hardware. So what ends up happening is we end up with a processor that looks like this. It should look very similar to the VLIW processor from before. The only difference is we've broken up the instruction fetch stages so that each individual lane has its own instruction fetch and its own instruction cache. So each cache is smaller, but this allows us to essentially allow certain lanes to shut off when they are not fetching and processing instructions. So this is a big idea. One thing you can see is after, for instance, this load word, we added the .sr mnemonic to turn off this lane, and you can see there is no instructions that are fetched during that time. The load word.sr and this load word would be next to each other in the code because there's no need to have no ops there. So that allows us to actually compress the code while we're at it. And you can see that the lanes resume execution when we encounter a load word.sr in lane 0, which just spins up the other lanes again. So that's the entire premise of this architecture. The front end, these look really scary, but they're just standard pipeline processor front ends. The only difference is in lane 0, whenever there's a branch that's taken, it'll send a message to the lanes that are not lane 0 saying, hey, resume execution. So that's what's going on there. Or sorry, update your value to your PB register. Sorry, the resume execution is the other change, which is right here. Whenever we enter the instruction cache, we peel off the most significant bit and just say, hey, if it's 1, tell everybody to suspend or to resume execution if you're suspended. Over here on the hardware for the other lanes, it looks very similar. There's a couple small changes. The first change is that I don't have to have a full BTB. I just have a register with a PC in it. That's a PB register. And I have a 2-bit register called the lane status register that suppresses PC updates and instruction cache accesses whenever the lane is either suspended or halted. So that's the main difference there. And you can see I peel off that SR bit to suspend if I ever fetch an instruction from my instruction cache that has an SR bit. Those are the main differences. There's a couple other small wires there. They are described in the paper. So one thing we had to do when we made this and we did all this really cool stuff was figure out how to compare apples to oranges. VLIWs and VLIW processors as well as the SLA processor, they actually, because we use a bespoke ISA, all of the ISA is actually the same between the two processors, but they still execute a different number of operations. VLIWs have extra no-ops to maintain alignment, as well as SLA processors have some administrative functions or instructions. So those administrative instructions, unfortunately, we don't execute those in the VLIW. So we have these apples to oranges comparisons. So instead what we've done is essentially pinpoint the instructions that are unique, namely the no-ops and these administrative instructions, and we just omit them from the results. Because what we find is all of the other instructions are identical, right? So what ends up happening is in the same number, if you execute n functions, they will execute the same number of operations and the same kinds of operations, aside from the differences in these no-ops and these sort of what we call meta instructions. So whenever we are looking at statistics, what we're going to do is only count non-meta instructions for performance, because the meta instructions, which are these no-ops and these these administrative functions, don't really contribute to the core semantics of the program. They're just there for correctness. So these meaningful instructions are part of the core control flow. They are shared between both processors, and in any window they execute of functions or branches, they execute the same amount. We verified that. I won't jump too much into that for time reasons, but they're there so I didn't make up a fake processor. So we use Spec06 benchmarks. If you're wondering why we use such old benchmarks, it's because it was very hard getting this thing running in the first place and making a new ISA and a new compiler and everything else. We warmed it up for 2 billion non-meta instructions and then ran for 10 billion non-meta instructions, these meaningful instructions. And we tried 2 SLA processors, one where we give the lane 0, which is always on, a larger instruction cache, and one where we kind of just equally distributed the instruction cache for the processor. we've evenly distributed it with the 888, and then lane 0 gets extra space with the 16844. We use an in-house assembly optimizer called ASOpt, as well as FastADL for our cycle accurate simulator, and Cacti 7 for power calculations. And we looked at both 4-wide and 8-wide configurations, but we'll only focus on the one. So meaningful IPC, short version, they're about the same. So that's really what it comes down to. We do it slightly better than VLIW, and that comes from the fact that while we have extra loads and stores from lane state management, our instruction cache misses are slightly lower per lane. Now, if you were to sum these numbers up, they'll actually be very close to that number, but one advantage is after a jump, multiple lanes can miss at the same time, so we can interleave requests to level 2 cache, reducing effective miss penalty. So what ends up happening is that we end up actually having very similar performance. The instruction fetch energy is actually reduced, and this is primarily the instruction cache, and we find because lanes shut off, if a lane shuts off or is suspended, we suppress the request to the instruction cache. Those instruction caches don't run. If all lanes are active, the SLA processor uses slightly more power, but as soon as a lane suspends at all, we start to gain significant power, significant performance when it comes to power. Total instructions encoded as well, because we don't have to encode no ops. What we find is that the SLA processor, again, significantly reduces code size. We have tried 4 and 8 wide. So the 8 wide VLIW, of course, is significantly larger. The SLA processors, however, use less instructions to encode the same amount of information, since they don't have to encode no ops. So kind of in conclusion, just so that I don't know how much time I have, but I'm trying to make sure I'm quick because I went over time. But short version, we made this proof of concept processor. It was meant to be not necessarily a full working processor. The VLIW and the SLA processor were pretty bare bones. But it's a nice proof of concept to show this new code generation and corresponding hardware is something that's actually practical and doable. We showed the SLA, at least out of the box, has similar performance to a VLIW processor, while really providing these significant reductions in fetch energy and code size. And we also delve a little bit into the scalability in the paper. Just can't do it really quick here. And really, there's two major things we want to work on in the future. The first is meta instructions do have a non-negligible amount of overhead, especially in function calls, because you have to keep track of more things. We want to aim to reduce that overhead as we move forward in designing sort of this SLA processor. The second thing is we actually want to target more state-of-the-art systems using sort of this, in quotes, multi-threaded architecture, because what we would like to do is really improve and work on this sort of idea of having these sort of parallel pseudo threads. So I want to thank you all. I appreciate it. And do you have any questions? All right, I got 1 million. Great.
Yeah, thanks. Maybe a very quick one.
Yes.
So you said that lane 0 would activate all of them at the same time, but that may not, I mean, you may have some...
Right, you might have some propagation delay, for instance, right?
No, but what I'm saying is that maybe in the schedule, you just want to activate lane 3.
Yes, so this is actually where sometimes we have to deal with a no-op. We just have a no-op.sr to put one lane that activates for one cycle back to sleep. Yeah, it's one of the only times where we kind of still have to use no-ops.
And very quick clarification for the evaluation. So you said that you only measured like the effective payload instructions?
Yes.
Would that, like the results that you showed, would they also, if I now measure the end-to-end, say the latency of executing the entire thing, will the results be the same? Or will these extra meta instructions?
Yeah, the meta instructions, yeah, we based it off, yes, they will map 1-to-1. So if you have in any window of time, the meaningful instructions are the instructions that are consistent for the both processors. And we ended up, I did a lot of work in actually testing that out to make sure that that measurement was correct. Yes.
Okay, yeah, I'll trust you.
If you're curious, I can talk about it offline too. Yep.
Cool. Yeah, very, very interesting idea. I guess the first thing that came to my mind is like VLIW with stop bits, right? Something like Itanium where you can compress no-ops. And I'd be curious, so specifically talking about iCache fetch, is that one thing about having a contiguous instruction stream of bundles is that, you know, your memory width response is going to be like 512 bits or something. Right. And if you have a bunch of contiguous bundles, you're going to have a lot easier time filling that compared to if you have to find, you know, if you have 4 lanes, you need to find 4 512-bit, you know, like, unless you're doing like fetch fusion without control flow divergence. Does this make sense? Where it might be easier to have better iCache behavior if you have contiguous instruction stream rather than 4 independent ones?
Yeah, so I completely understand where you're kind of getting at it, is they're all over the place. So one thing that's kind of useful is because the instruction streams they're contiguous in the lanes that they are in. So lane zeros, all of their operations are still contiguous in memory. So what we found is, at least within the simulations that we were testing it out, that there is what we end up doing when we lay it out in memory is having lane zeros code followed by lane one's code followed by lane. So oftentimes, especially in smaller functions, you end up getting a lot of the same performance. It ends up not being a significant impact, especially because lane 0 is always running and it ends up getting those benefits so that when you fetch something, it takes longer for one of those lanes to actually end up missing if you are not having a branching control flow. That was at least kind of the, I think I might have answered the question.
So if I could just follow up a tiny bit. I think that makes sense. My question would be for when you do have a lot of control flow, and you're trying to at least be able to access everything in your lane before you branch off somewhere else. Having a contiguous instruction stream across all the lanes allows you to fill that better, right?
Yeah, that's a good point. That might take a little bit. If you would like, I'd love to chat with you after.
Sure.
That might be that's a longer kind of answer.
Yeah. But very interesting thought. I think this is a cool idea.
Yeah.
We can take more questions.
Yes.
Right. One more.
Yes.
Very briefly, I'm not entirely clear how you're handling control flow. So you're saying only lane 0 can handle control flow. So no problem. In VLIW, often only op0 can handle control flow. But in a VLIW, I only have 1 program counter to set. Here I have 4 or 8 to set. How does it work?
Okay, so short version, I'll come back really quick to let's go to the hardware and corresponding software. So short version is lane 0 is the only lane that has access to the BTB. Right? So lane 0 here, if I access the BTB, and let's say I assume or I predict a taken branch. We're going to broadcast that information to each lane. And lanes, say this is lane 1. All that's going to happen is there's going to be an incoming signal from lane 0 here. All right? And what might happen is if I predict taken in lane 0, all other lanes have an instruction called a prepare branch instruction that before any branch is taken, they'll all get one. And if a branch is taken, that says, okay, now copy the PB register into the PC and just start executing there. Naively, you don't need to know why, you just need to be told to do it. Okay, got it. Does that help a little bit?
Yes, of course it does. Thank you.
Glad to hear.
Let's thank our speaker once again.
Thank you.